circle, this nice bright circle, a very sharp feature, and then surrounding some central dark depression, right? And those words, right, the sharp bright circle and the central dark depression, those are things that are very universal, turn out to be very universal, right? So how do you show that? Well, you simulate a whole bunch of different kinds of plasmas, and you look at their emission, you look at the light, you look at the images that you get from that, and you see that the images are going to be wildly different, but you always have this bright ring here, and you always have a central dark depression. So the name of the game is then, if you really want to know something about the geometry, is to look at these things that are universal across emissions, because those are really signatures not of the plasma, but of the geometry, right, of the black hole itself or the object itself. And so in particular, this bright ring here is what's called the photon ring, and certain properties of it, so its shape, also its thickness, which is related to certain critical exponents. These are all properties that you may think, or you are, right, you can show this, are universal and don't depend really on the emission, right? And so Alejandro will tell you more about a particular critical exponent and how we can or cannot measure that in potential future experiments. Okay, so what I'm going to talk about is this photon ring, right? So let's focus first a little bit more on the observation of it before I actually tell you where it comes from, sort of in a theoretical way. You have a question, yeah? Why is it a circle?
Yeah. Are we looking at the black holes?
Yeah, no. Maybe let's. I can repeat the question. Why is it? Why
is it spherical?
Yeah.
Sorry.
So your question is, why is it a circle on the view screen?
Why is it a circle?
Yeah. I'm gonna talk a lot about the shape of this guy. So maybe ask me later if you want. But it's a good question, right? Because in principle, you might think that depending on where the plasma is and how you're looking at it, and also how the black hole is rotating, you might see something different. But it turns out that it's a very sharp prediction of GR that you will actually always see something that is approximately a circle or even an ellipse, which is a little bit crazy, right? But that's a signal of the warped space-time, of course. No, okay, the question is, I'll repeat the question, Nick, it's okay, you don't have to throw it. The question is it a non-rotating black hole? No, this is a Kerr black hole with A is like 0.95. We're looking at it at about 17 degrees inclination, so that means you're almost along the degree, almost along the rotation axis. But even if you go to, well, okay, I'll show you pictures in a minute of like looking at it equatorially. It still looks almost like this, right? Okay, I'm happy to take questions, and I'll repeat them unless they're very long, so that Nick doesn't have to throw out his arm on the first day. So what do we actually measure, right? And I think this is really important to sort of emphasize, because when you want to make a statement about, okay, I'm going to go out and measure something beyond GR, of course you have to have in mind how are you actually going to measure this, right? And so in particular, this photon ring, like I said, it's a very bright and very sharp feature, which means that when we actually go out and measure it, this will also show up in our measurement as a very bright and sharp feature. Now, however, we don't actually see this, right? We don't measure, when we do black hole imaging with VLBI, very long baseline interferometry, we don't measure the image, we measure, or we observe in Fourier space, okay? So we actually observe the Fourier transform of this guy, of this image, and which looks more like this, right? So this is like the Fourier transform of, let's say, a slice, right? Let's say it's like a horizontal slice. And so it looks something like this image. And so how do I translate then the fact that there's a bright, sharp ring here? Well, sharp features mean high gradients, and so that means something interesting happens in the high frequency domain of the Fourier transform, right? So we need to look here on the right side, right, on the right side of the plot, which is where the high frequency stuff goes, the high baseline lengths, right, large baseline lengths, which means you need telescopes that are very far apart to measure these things. Okay, so what I want to basically emphasize is, when you're looking at this image, there's going to be features that depend on the plasma, right, which are not very sharp, and they're going to be dependent on whatever the plasma is. That's going to be the low frequency stuff. That's going to be the stuff over here, right, on the left-hand side of the image. By the way, EHT, only observes like a very small fraction on the left-hand side here, right? So to observe all of these high frequency things, high baseline things, we need satellites in space to be able to see this, which I think maybe Alejandro will say more about as well. possible emissions. But anyway, so the stuff over here is very plasma dependent, right? This depends on the emission. But like I said, this sharp photon ring here, if you have access to these high frequencies, these long baseline lengths, then you can really resolve, you resolve out basically all of this stuff that depends on the plasma, and you really kind of are looking at the geometry in some sense if you're looking at these long baselines. And so in particular, right, you might wonder about something as basic as the diameter, the distance between these two peaks. Remember, we're looking at a horizontal slice here, and so the distance between these two peaks, d, the diameter of this photon ring, is encoded in. If you zoom in here, you see there's wiggles, right? These periodic wiggles have been shown that they encode exactly the. They encode exactly the this diameter in this sense, right? It's basically this sine function where the period depends exactly on the diameter, right? This was shown, well, not originally by these guys, but they talked about it a lot. And so, right, so my point here is really like, okay, this is something I can go out and measure, right? I can really measure the diameter of the photon ring, because if I have this access to these baselines, I can look at this signal, I can look at the period, and I can extract the diameter from this. So it's a good observable in that sense. Okay. All right, good. So where does the photon ring come from? Well, the photon ring comes from nearly bound orbits, right? So because we have a black hole, we know that light gets bent a lot, and light can even get bent so much that it can form bound orbits, which means that you can, if you shoot the light exactly right at the black hole, it will stay orbiting the black hole forever, right? Which is something, of course, completely crazy for us, right? Because we're not used to thinking of light being bent in such a ways. However, these bound orbits are unstable, which means if you shoot light a little bit differently, right, a little bit off of this bound orbit, what it's going to do is it's going to follow this bound orbit a little bit, right? So it's going to rotate around the black hole maybe a few times before escaping eventually, either escaping or falling into the black hole. And so the photon ring is exactly due to these nearly bound orbits. So you have light that is emitted from around the black hole, right, from the accretion disk, for example, and it happens to be trapped on these, or nearly trapped on these nearly bound orbits for a few orbits, and then it escapes and eventually reaches our telescopes, right? That's sort of the picture that you should have. And so, yes, and so that gives us basically this bright ring here of photons that come at us. Okay, I'll talk a little bit more about where it exactly comes from later, but it does happen, right? If you look at this for different inclinations, right, meaning different viewing angles with respect to the axis of rotation, when you make the rotation of the black hole itself larger or smaller, you'll get different shapes of this photon ring, but they're all going to be roughly the same, right? So you can kind of see the green. Over here, I've plotted a bunch of the shapes, and so this green dotted line is Schwarzschild, which is just zero rotation, so it's just a circle. And sort of the most extreme you can have is if you're looking at extremal Kerr head-on, which means, sorry, not head-on, but in the equatorial plane, right? So then you're really looking perpendicular to the rotation axis, and that's this red curve here. And so you see it's a little bit, not as circular, and there's this nice straight part here, which is very interesting, but it's not that far away from being a circle or an ellipse. And that's just a consequence of looking at, what are the bound orbits in the Kerr spacetime, and how do you shoot rays, let's say, right, from my view screen asymptotically, how do I shoot rays backwards in time to get onto these bound or nearly bound orbits? Okay, so in particular, what I've plotted here is not the photon ring itself, the nearly bound orbits, but actually the image of the bound orbits. Okay, so if I look at all of the bound orbits in Kerr, and I ask myself, how do I reach them by shooting geodesics from my view screen at infinity? How do I reach them by shooting photons? Then the answer is one of these curves, right, depending on the rotation of the black hole. And this is something that you can determine analytically, right? And it's called the critical curve. So the critical curve is the image of the bound orbits around the central object. And it's, for a lot of purposes, it's easier to think about this critical curve than it is about the photon ring itself, even though the photon ring, right, is the thing that we observe. We observe the nearly bound geodesics, of course, not the bound geodesics. we observe the photons that come from the nearly bound geodesics. This is more just a mathematical structure, which of course underlies the photon rings, right? So this guy is going to hug very much the critical curve, and that's why, as a first approximation, it's interesting to think about this critical curve. Also because we have some analytic control over it, right? Especially for Kerr, we can really write down some analytic or semi-analytic expressions for this. All right.
So this is
Yeah.
above the unstable circular orbit?
I'm sorry?
Is this above the unstable circular orbit?
These are all unstable spherical orbits in Kerr.
There is a usual unstable circular orbit, right? This is just, this critical orbit is above or?
There's many bound orbits. Okay, so the question is about these bound orbits. So in Schwarzschild, you just have one orbit, which is at RS3m. Right. In Kerr, you have a whole range of radii where you can have bound orbits to shoot on. And so I'll talk about that later, but one of the really crazy things is so every point on this critical curve, as you move around, so a different angle on this critical curve corresponds to a different radius of bound orbit. So as you're moving around an angle, right, on your view screen, you're actually probing a different radius near the of bound orbit near the black hole, which is kind of crazy. Yeah, okay. And so why am I interested in this? Well, again, I'll go back to the question I originally asked, right? If I have something that's not Kerr anymore, right, but it's sort of very near Kerr, or it mimics Kerr, it has structure, it's a different black hole, it's a different object, I want to kind of wonder, these photon rings, how much can they change? Okay, because a lot of work has been done in understanding how the photon rings look for Kerr, for GR. But not a lot of insight. We don't have a lot of insight as to how robust those statements are. And in particular, if I deviate a little bit from Kerr, will this show up in the photon rings or not, right? Is this photon ring just something that all black holes have and is always the same or not? Right, so how universal are the properties that we know of the photon ring for Kerr beyond Kerr? And so I'm going to focus on the critical curve, and I'm going to focus on a few very basic aspects of this critical curve, which again is like the underlying curve of these photon rings. I'm going to ask myself, is this connected? Is this always going to be a connected and closed curve? Like we see here in Kerr, it's obviously a very nice, almost circular curve, so it's connected and closed. And so the reason or the motivation for this is because, on the left here we have Kerr, here we have some black hole called the Manko-Novikov black hole, which is some non-Kerr black hole. And here we have a fuzzball actually, so it's a smooth geometry. And you can clearly see that the photon ring is not necessarily, or doesn't seem to be necessarily, this nice, simple connected curve, right? Here we have something that looks kind of like the Kerr curve, but then here we see this, secondary kind of photon ring inside. Right? So it seems like you have not just one connected component. And here, of course, it's very clear you seem to have multiple photon rings, right, if you can call them that, that underlie the image here. And so I'm going to ask myself these basic questions, connected or closed, and also, okay, let's say we do have just one curve, is it always going to be the same shape as Kerr, right? And so I'll actually focus on that question first. Let me just, I'll be right with your question maybe. Let me just finish this. And so the questions that I'm going to ask also in this order are, I'm going to first focus on the shape. So I'm going to ask myself, look, this shape here, how much can I actually deviate from the Kerr or GR prediction for the shape of the photon ring or critical curve? And the second question that I'll ask, if I have some time for that, is there some relation between this critical curve or photon ring being one nice closed and connected curve and the issue of geodesic separability, right? So I'll talk about that later. Yeah.
I thought that for a realistic puzzle, the geometry outside is well approximated by Kerr, and even if the correction is 1 over the entropy of the black hole, the photon ring would be identical.
Okay, So the question is, for a realistic, isn't it true that a realistic fuzzball should look exactly like a black hole, basically, right? Okay, so I'm sure we'll have a lot of discussions like that this week, but for my talk, I don't really care, right? So my talk is really, I just want to know what is possible in principle, okay? So if I replace a black hole, or I replace the Kerr black hole by a different black hole, like I did here, I want to know, how much do I need this black hole to deviate from Kerr before I can see signatures in the photon ring? And the same thing the same question for compact objects, right? If I replace the Kerr black hole by some compact object that is not exactly Kerr, then how big does it need to be? How much does it have to deviate from Kerr before I can actually see deviations from the Kerr picture? Okay, and so yeah, if you have a fuzzball geometry which looks exactly like the Kerr black hole outside of the horizon, then you're not going to see a difference, right? That's sort of obvious. Or okay, maybe it's not obvious. We can even discuss about that because there's the issue of like transparency and everything. But okay, but that's not my question, right? I'm agnostic as to what is in the middle of the space-time. I just want to ask the question: how much does it need to deviate from Kerr to be able to see a signature of that in black hole imaging? Yeah.
It's a question of how much it needs to deviate at the scale of the photon ring, not
Yes.
near the horizon.
That's right. That's right. Yeah. Yeah. So the photon ring is going to be, I mean, it depends on your, so if you just talk about Kerr, right? So the photon ring is sort of dictated by the bound orbit structure, right? And so for extremal Kerr, this goes all the way to the horizon, of course, but otherwise you're sort of outside of the horizon. Yeah. Some finite distance array. Yeah. Any more questions before I go on? Happy to
Can I
take
throw
them.
the cube at anybody who has a question in the future?
All right, good. So let me focus on this first question then, right? So sort of a very basic question here. What is the shape of this guy? So what was shown by Gralla, Lupsasca, Morone a few years ago, and also by Gralla and Lupsasca in a more theoretical sense before that, is that the critical curve shape, which is to a very good approximation the same as the photon ring shape, as long as you're going to at least the NS2 subring, which I won't talk more about. But basically, right, the photon ring shape is about the same as the critical curve shape, which I've talked about. And it's this thing called the circlipse. So what do I mean by that? Well, if you measure, so first of all, what do I mean by shape? Well, again, remember we could measure, right, a good observable was measuring the diameter of the photon ring. And so you can imagine measuring it not just along this horizontal axis like I did before, but measuring it at different angles phi, right, as you sort of take phi to be from 0, so that's horizontal, over to pi. And so if you do that, right, you measure the diameter of this photon ring over different angles, you'll end up with a plot that looks kind of like this, right, so phi on the horizontal axis and the diameter on the vertical axis. And whatever your details of your Kerr, meaning whatever the spin is and whatever viewing angle you're looking at it, it's always going to look like this. It's always going to be this nice bump function, right? So you have, it's always going to be periodic in pi, right? Because you're measuring the diameter. So the diameter at 0 degrees and at pi degrees is the same because you're measuring the same thing. And so it's a periodic function in pi, and then it's going to have a bump in the middle. And so what they showed is that this bump function is, to a very good approximation, or is basically predicted by GR to follow the shape of a circlipse. So what is a circlipse? It's this functional form here. Basically, if the square root wasn't there, it would just be that the diameter is a constant, right? So that's just a circle. Circle is a constant diameter no matter at which angle you measure it. If this first R0 isn't there and you just have the square root, that's actually the equation for an ellipse, right? So an ellipse is where the diameter, of course, changes as you change your angle where you're measuring the diameter, and it turns out to be exactly this form, right? And so they showed that, you know, for the Kerr critical curve, you always have this thing where you have basically sort of the circle term plus the ellipse term, and so they call this the circlipse. Okay. And so this circlipse has 3 parameters. If you forget about this little offset phi 0, which is just telling you sort of where to start, where to put your 90 degrees, then it has 3 parameters, R0, R1, and R2. And what they showed is that, you know, by fitting the data, which are these points here, so that's like a simulated observation, by fitting that to a circlipse function, you can get something, the GR prediction should match the actual shape, should match the actual points within an accuracy of about 0.04%. Okay, so the upshot, right, the upshot of what they were trying to say is that, you know, if you measure this diameter over the different angles, which is something you can actually go out and do, then the GR prediction, you should be able to confirm GR with something that is about 0.04%. Okay, so that's pretty nice. But what we also showed then in a paper last year, so this was together with a bunch of plasma physicists and also my master student, Seppa, who's now in Cambridge, is that, well, actually, it seems like this doesn't, okay, this is a nice consistency test of GR, right? Because, you should find this Circlipse function within, it should match within, 0.04%, which seems like a very rigorous test. But it doesn't really tell you anything about, is this Kerr or is this not Kerr? And what do I mean by that? Well, we looked at a bunch of black holes that are not Kerr, and we saw that also them, as long as they're not wildly deviating from Kerr, they will also have a Circlipse, right? The Circlipse function will also just match their photon ring, their critical curve very well, right? So you really need to have an enormously large deviation from Kerr to break this Circlipse shape in some intuitive sense, right? So, and of course, if you have an enormously large deviation from Kerr, then why are you even going to measure this the shape of the photon ring? You'll just see that it's not a black hole, right? You have a question?
What am I supposed to do?
Talking to the microphone hole, yeah.
No, so my question is, in this beyond Kerr black holes, you say that they also satisfy this Circlipse
Right.
function, but are the coefficients R0 to A2 different from what Kerr is?
Yeah,
What's
so,
predicted?
right, so basically, but the coefficients are not predicted by Kerr. Okay, so I don't need to repeat the question. The coefficients are not predicted by Kerr, they're just predicted, it's just predicted that it's going to be this functional form. And so as long as you can find coefficients for which, you get a nice graph that matches your data, then you can't really say anything about Kerr doesn't predict it. That's basically the statement, yeah. There was another question.
One over here.
Oh, okay.
So this 0.04% accuracy
Yeah.
is assuming that one knows the plasma and...
No, actually no. So this is assuming, okay, this is sort of in the details of this paper. This is assuming that you have a large enough baseline that you can measure the NS2 ring. So these are photons that have traveled 2 half orbits around the black hole before coming out. And it turns out that because you're measuring this NS2 ring, which is at very high baselines, this is very independent of the plasma. So they did a lot of different simulations, and they show that you can basically always do this very robustly. Yeah.
Can you be more precise about what you mean by large deviations from Kerr? Because, of course, there's many ways. I mean, if you just change something that's essentially a radial profile of the gravitational potential, or are you making it also highly non-spherical?
I don't have any actual pictures, but yeah, I mean, there's many different things that you can do.
Yes.
But I guess what I'm trying to say is that even something like this, which you can already kind of just by eye see that it's different than Kerr, this still has the Circlipse shape, right? If I forget about this little
But that's
guy.
because the object is essentially still roundish, and the potential is not that different.
Well, exactly. But if you have something that's very non-spherical, then, or very non-round, let's say, then this will show up in the image, right? You'll get something that looks
Yes.
more like this.
But then, is that something that you have tried as well?
Yeah, but the point is, right, if I'm looking at this, what's even the point of saying I'm measuring the diameter of the photon ring? Because there's like multiple photon rings here. So I'm not even going to have a clean measurement of the diameter.
Okay.
Right, so the whole premise, let's say, of what I'm doing kind of breaks down if I'm very far away from Kerr anyway. Yeah, that's kind of the point. Yeah, I mean, we can talk about like exactly how much you need to deviate away. So, for example, I mean, what we studied in this paper was the Johansen black hole and the Manko-Novikov black hole. So they break, especially Manko-Novikov, it breaks spherical symmetry very much.
Sorry, Daniel. For
Yeah.
Kerr, what is the relation between R0, R1, R2, and the mass and the spin? For Kerr?
It's not an obvious relation, and so I don't think anybody's really even derived a certain relation. It's just that you can show that all of the Kerr black holes follow this form. Essentially, what you do is at low a times sine theta, so either low spin or low inclination, you have exactly right. You can derive the ellipse form, and then it's more of an empirical statement that if you make it the Circlipse, that you will cover the entire parameter space to within 0.04%. Yeah, but there's no clean relation between these parameters and M and A, let's say. Yeah. I mean, M, the mass of the black hole, basically sets the scale, right? So that kind of sets the overall scale of this, and then the relation between the parameters is determined by your inclination and your and your spin of the black hole, but in a very nonlinear way that we don't have any analytic control over. Okay. So, get closer again. Okay, good. So what we did, so what we were trying to do this year, Alex Lefosca and I, was to basically start from first principles about this function, right? And so from first principles, this diameter function as a function of angle, well, it's a periodic function in the angle phi, right, with a period pi, just like I said, because we're just measuring this diameter. And so that kind of just means that it has to be expandable as a Fourier series, right, which I write here. Now it turns out, and this is a very surprising fact of the Kerr geometry, that your critical curve is always going to be reflection symmetric. There's always a horizontal symmetry axis of this critical curve. Okay. Now I'm expecting that people will be confused by this, but okay, we can talk about it later. Maybe this is true. Your critical curve always has this horizontal reflection axis. What this means in terms of the Fourier series is that there are no signs here. Good. So so there's no signs. And moreover, right, you can sort of see it should be a smooth curve, right? You expect that there's no cusps or sharp kinks in it. And what that means in a Fourier language is that there's going to be some at least polynomial fall off asymptotically of these Fourier coefficients. And so maybe it's not so surprising then to say that, you know, a very good approximation is probably just taking some kind of, let's say, second order approximation here where I'm only keeping the first two Fourier coefficients. Right, that seems fairly reasonable as an assumption because smoothness is basically going to tell you that the Fourier curve coefficients are going to die off, and so probably right maybe from C3 on they're not so important anymore. Now you might wonder why exactly two Fourier coefficients. Well, if you look, if you now compare what we have from just our simple Fourier series to the circlipse, right? The circlipse is also determined by just two parameters if I sort of take out the overall scale, which I've also done with my Fourier series. And so you might just think like, well, okay, basically this is explaining why the circlipse works so well. It's because you have two coefficients, C1 and C2 here. You can make them anything you want, and they correspond to making R1 and R2 of your circlipse anything you want, right? So this is basically telling you to a 0th order why the circlipse works so well, even beyond GR, to look at this shape of the photon ring or of the critical curve. It's simply because it captures all of the information of the Fourier series to second order, right? And that's all you really need for this nice smooth curve. Now it's a little bit more complicated than that, although this is roughly true, and it also helps to explain the errors that we have, right? So I mentioned that you can always fit the circlipse within about 0.04% if you're looking at the NS2 ring. And this is exactly the order of magnitude, right? The fit errors that you get from the circlipse is exactly the order of magnitude that you would get from this Fourier series when you're saying, well, I'm actually forgetting the higher order coefficients. And so in particular, C3 is about of this order. So the third Fourier coefficient. However, there is, of course, the fact that a circlipse is not a general Fourier series, and so this is a much more general formula, right? Because I can use any C1 and C2 that I possibly want, and in particular, if I look at all of the possible C1s and C2s that the circlipse function gives me, it's actually just a sliver in C1 and C2 space, right? So C1 is on the horizontal axis, C2 is on the vertical axis, and so everything that's white is let's say one of these guys, right? One of these d5 functions that is not captured by the circlipse. Everything that's in the blue region here is something that is mappable to a circlipse function. So it's actually a little bit trickier because the circlipse, it seems to be a sharp prediction of where in this Fourier space that you should, in this Fourier series space that you should actually fall. However, we can sort of reverse that argument, and we can kind of say like, okay, but how do I cut away in this allowed region of diameter functions, right, of my d phi, to get something that is more like this circlipse, right? So in other words, what kind of physical conditions can we put on our diameter function to reduce the allowed region? Okay, and the reason why we want to do this, of course, is we want to understand how exactly do you deviate, how exactly would you go deviating from GR? Okay, so the three conditions that we found that seem very reasonable if you think about what the critical curve should look like is, first of all, this diameter is a diameter, so it should always be positive. I think that's obvious. What's maybe less obvious is that you want to stay, of course, within the realm of something that looks approximately like GR. And in GR, we know that there is a very narrow range of diameters that's allowed. What I mean by that is it's always going to be, not too elliptical, basically, right? And so if we kind of put that in as like, okay, we're gonna limit the range of the diameter as the function evolves, right? To discount things that look like these crazy ellipses, then that puts, of course, heavy restrictions on our function. The other thing that also seems very reasonable is to not allow things like cusps or self-intersections of the critical curve, because again, if we would see something like that, that would be a very clear smoking gun of GR, right? So that's something that we can physically get rid of. And then the third condition is maybe a little bit less clear, but remember I said that the d phi function always looks like, it always goes from its minimum value to the bump at pi over 2 and then goes back down again. And so, one way of interpreting that is that, the bump or the maximum really has to be at pi over 2 and it can't happen anywhere else. So the maximum diameter, right, if we're thinking about what the actual curve looks like, the maximum diameter has to be on this vertical axis. That is true certainly for all of the Kerr black holes. And so this is an example of something where you can see that it's not true because the maximum diameter is sort of this diagonal here. Right, and it's kind of like almost a stronger condition than asking for no cusps, right? You can almost see that this is like a sort of an onset of a cusp. Okay, again, this is, you might think like, well, why do you want to discount these guys? And the reason is really just we want to understand, what does GR predict for us physically, let's say, right? And so this is kind of the interpretation, let's say, of our condition. Okay, good. And so what do we get when we put these three relatively reasonable conditions? Well, we cut away all of the white space here, and we're left with only this blue bow tie shaped space. And now we see that actually the allowed region, which is the C1, C2 space of the blue region, is almost completely covered, at least in the lower half here, by the circlips winks, the circlips slivers, which is the red region. And so, right, there's a little bit of region here down below, but that's really, really small. And so anything that you would take in this blue region down below will differ from a circlips by a very small amount. So the circlips will still be a good fit. And in fact, the maximum deviation that you can get is, right, so the maximum distance, let's say, between a point in the red region and a point in the blue region is about on the order of 2%, which is still relatively large, but it's already, getting to be quite small. Now, of course, this should not come as a super big surprise because we've, by hand also put in that the range of d phi is limited, right? So if we have a low, we've sort of put in already that the d phi can't deviate too much, and so obviously this whole region here is just very small. Okay, so what I want to get out of this, right? And so if this was maybe a little bit too technical, is a recipe for how to break GR, right? From the perspective of this shape of the photon ring or the critical curve, right? How do we break GR? How do we go beyond the circlips parameterization? How do we get a shape that looks definitely different from GR? Well, we need to have one of these things, right? We need to have either something with self-intersections, right? That's obvious, some kind of a cusp. We need to have an extreme range of diameters, meaning like a big ellipticity. We need to have something, right, one of these things, right? You don't need all of them at the same time. Or you need to have something that's very wiggly, meaning we made a mistake in throwing away the higher Fourier modes, right? So a curve that goes wiggle, 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 or all around. Those are all possibilities. We can also break the reflection symmetry of the critical curve. So like I said, there's always this horizontal reflection symmetry, which is a firm prediction of GR. If we break that, then that means there's going to be signs in our Fourier expansion. And then the final thing, which we don't really have a nice interpretation for, is, as I said, the circlips kind of covers the lower half here, but we don't really understand why we're allowed to take this Fourier coefficient to be positive but but this is not in the circlips. So somehow this is also a way to break GR if you can measure a second Fourier coefficient that's positive. There was a question.
Then can you please? I got it. Can you please explain why the circlips is like not allowed in the region? In principle, like why is the circlips not covered by the blue always?
Why is the circlips not? Why aren't there circlipses
so
up
you
here?
see, there is like one part of the circlips, the orange here at the edges, that is not covered by the allowable.
Oh,
region.
okay, yeah. So I wasn't very careful in my graph, but basically the circlips is bigger because I'm still graphing, although it falls off of the graph that I'm showing here. I'm still graphing all possible circlipses, and so all possible circlipses also include circlipses that actually break this this assumption. So if I was better at graphing and I took a little more time, then I would have also cut off the circlips exactly here, right? So it would just be an overlap, yeah, a strict overlap, yeah. Yeah, thanks for the question.
What's the origin of the Z2 symmetry that you've been talking about?
Yeah, okay. So this is a very mysterious thing. So even though if you might think that if you're looking at Kerr at some weird inclination angle, then you would get a critical curve that is not reflection symmetric, right? Because you're looking at it in a very non-reflection symmetric way. Nevertheless, if you trace the bound orbits, you will always get a critical curve that is reflection symmetric, horizontal reflection symmetric.
But with some weird shaped fuzzball, I could probably get something that breaks it.
Right, so there's a result that says that if your geodesic equations are separable, this is always true, you always have this reflection symmetry, which again is a completely weird thing because you could have something like Rashid Larson or something that breaks reflection symmetry in the metric even, right? Kerr is reflection symmetric in the metric, but you could break it in the metric, look at it, even equatorial, you see differences up and down, and still the critical curve has to be reflection symmetric in these geodesically separable spacetimes. I think that's intuitively, I just don't have an explanation for that, but it is a mathematical fact. And so yeah, so I think this is a very interesting thing, right? Because that also means that if you find a sign, right, meaning you break reflection symmetry, that is not just indicative of you're moving away from Kerr, but it means you're moving away from separability in your geodesic equations, right? It's a very strong statement about the underlying geodesic equations, which I think is kind of interesting. Yeah, there's a question over there.
No, just so the statement that you just made about that it's indicative of breaking breaking the separability. That's only true for the critical curve, right? It's not true.
That's right.
For
yes, that's right.
Circlips, so for the.
That's right. Yeah. So what I've said about the reflection symmetry is a property of the critical curve. Of course, if you look at photon rings, even for Kerr, and you look at them from an inclination, they're going to be asymmetric. Yeah. But if you look at higher and higher photon rings, of course, because they're hugging the critical curve better and better, the higher the photon ring, the less breaking of reflection symmetry you'll see. Yeah. Actually, it's a very interesting story. So logically, the photon ring that has the most asymmetry is if you're looking at it at a sort of a relatively low inclination and you're looking at n as 1, right? This is the most sort of lop-shaped. However, what's interesting is because you're at such a low inclination, you're actually sort of in a almost head-on. And if you're head-on, it's going to be a circular shape, right? Everything's circular. And so moving away from that circular shape actually gives you a vertical, an approximate vertical symmetry axis. Which means that, okay, we could talk about this later. It's actually really interesting. So it means that you will have a reflection symmetry and you will not have any signs, even for the n as 1 ring, but not because of the horizontal symmetry axis, but because you have an approximate vertical symmetry axis, which is unexpected until you think about it. Yeah. Yeah. That's fine. Yeah, you want me to stop at 50, right?
There's been loads of questions. I'm just saying.
Okay.
If you're running halfway through, I'd be worried.
Well, I mean, the next part goes quicker. So, also, cut me off when you. Well, give me a 5-minute warning. Let's say. Okay, so this is sort of the end of this part where I wanted to talk about the shape of the circlips, right? And I wanted to give you some, this is a very basic thing in some sense, right? You will go out and you measure this diameter, which sounds like a really silly thing to do, but it is something that you can actually do, right? And it is something that is not dependent on, again, the plasma emission. So it's something that you want to go out and do. And then you can ask yourself, well, how do I break GR in this actual shape that I'm going to be measuring, right? And that's kind of what we wanted to investigate. Okay, so any more questions on this before I move on? Okay, so the next question that I want to ask is something even more basic, right? So now I was talking about, okay, well, let's say we have something that's kind of Kerr-like, right? But maybe this shape is different. Now I really want to ask the very basic question, well, okay, this critical curve, or the location of the photon ring, is it even going to be this simple, connected or closed curve? And it seems that there's this relation between the connectedness of this critical curve and geodesic separability, right? And so in particular, right, on the left we have Kerr, so a nice simple critical curve. And these two guys have non-separable geodesics, and you can see that it seems like if I would define some kind of critical curve, it seems like it wouldn't be a nice circular connected curve. And so there's a bunch of questions you can ask, but the first question you can ask is, well, okay, what if we do have separability? We have a most general separable metric possible. I don't even know what it is, but some separable metric, so some metric where the geodesic equations separate. What's the most general possible critical curve? And that's even a question that we don't really know the answer to yet. So, yeah, okay. So let me, to talk about this, let me first review a little bit how you get to the Kerr bound orbits and the critical curve. Okay, this also answers, I think, a little bit the question about what the shape is. So in Kerr, we have, of course, null geodesics, which have two conserved quantities, the energy and angular momentum, which come from the killing vectors of the Kerr geometry. There's also another constant of the motion, which is the Carter constant, which, of course, is exactly what you need for separability of the geodesic equations. And what's interesting to note is that, between L and Q, right, so angular momentum and Carter constant, rescaled by energy, but whatever, there is essentially a one-to-one map between these conserved quantities and coordinates on our view screen, right? So we have a screen at infinity that we're using to look at the black hole, and the coordinates on this map to one-to-one map to different values of L and Q, essentially. So what happens in Kerr is that I can basically write separability means I can write the radial and the angular, right, the theta equations of motion as two separate equations that don't really couple to each other, right? So the evolution of the r coordinate and the evolution of the theta coordinate are governed by these things called the radial and angular potential. And in particular, right, the radial potential is only a function of r and, of course, the coordinates on your view screen, right? So different geodesics have different radial potentials. So this allows us also to write down, very nice relations that kind of say, some radial motion, right, an infinitesimal radial motion is related to some infinitesimal angular motion. Okay, good stuff. So what happens now is by studying, of course, this radial motion equation, I can deduce where the bound orbits lie. And in particular, you can show that the bound orbits only lie at double zeros of this radial potential, right? Essentially, you need r to be 0 so that dr is 0, right? The radius doesn't change. And then you need r prime to be 0 so that the equation of motion, right, d squared of r, is also 0, right? And so it stays at the bound orbit. Now this, of course, gives you an equation to solve for possible coordinates on the view screen, and you end up with finding the critical curve, right? So this is the simple procedure that gives you the critical curve in Kerr. Okay, and it also tells you that, if you then think of the angular potential, you and look at what the geodesic on these bound orbits will do, is it will oscillate between some minimum value and some maximum value, right? And so this leads to the nomenclature of saying, one orbit is basically one full theta oscillation from theta minus to theta plus and back again. Okay, so that's an orbit. Okay, so I'm going a little bit fast because this is a little bit review, a little bit simple / not super important. But the picture that you get in the end is you have this thing like that's called the photon shell, right? And so this depicts sort of the bound orbits, right? So if you pick one radius here, then you have an orbit that bounces between theta plus and theta minus as it travels around the black hole, bounce, 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 and stays on the same radius. And if you then look at how this maps to your critical curve, this is something that I said before, if you take a different radius of bound orbit, this maps to a different point, right? A different angle along the critical curve, which again is something really crazy, right? If you just travel around a critical curve, you're changing the angle at which you're viewing, but you're probing a different radius in the black hole geometry. Okay, so this is the Kerr story. And then you can ask yourself, well, okay, this was my Kerr story, right, that I just told you about. You can ask yourself, well, how does this change when when you go to something that's not Kerr anymore, but is still separable, right? So that's kind of the name of the game. Okay, let's now generalize this and say we're not in Kerr anymore, but we are still in a separable metric. And so in particular, right, you can start going through this reasoning again, and so obviously you will still have a separated equation by definition. You're still in a separable metric. So you can still look at the radial motion, but is it obvious now that you have bound orbits that are only at a fixed radius r? In principle, a priori, you could have bound orbits that go between some r minus and r plus and sort of oscillate between those, right? You certainly have that for time-like orbits, right? When you have planets, for example, right? They can oscillate between, they have some kind of elliptical orbit. So is this always going to be true in the separable metric? Let me sort of skip over that. And let me also ask the question, do you have a critical curve? In other words, will you always have a nice, connected and closed critical curve? That's also a question you could ask. And so this is something that has been studied before, but I would argue that the results were not complete. And so we're nearing, let's say, a proof that yes, indeed, this is actually the only possibility that you can ever have in separable metrics, is you can have only these so-called spherical orbits, which are at constant r. And so this kind of oscillating orbit is not possible. The only thing that we haven't been able to discount yet is a very specific kind of orbit called an open orbit, where you would have radial and angular turning points, right? So turning point being where you go from going increasing to decreasing, which would be coincident, right? And so these guys we're not quite sure how to get rid of yet. Okay, that's perfect. And then the second question, right? So this seems to be true, although we're not quite clear that. And once you get only spherical orbits, right? Once you say that the only bound orbits in your geometry have to be at this constant r, that's a double zero of the radial potential, it's actually fairly easy to see that your critical curve has to be a nice connected curve, or at least has to exist in connected components. And basically the idea is that you certainly have escaping orbits, let's say, right, which have one radial turning point. Right, these are orbits that are like, if you shoot your geodesic very far away from the black hole, it'll get a little bit closer, but then maybe be deflected a little bit, but it'll escape to infinity, right? So it has one turning point. And you also know that there has to be infalling orbits which just don't have any radial turning points, and so that if you have the going straight to the black hole, it will fall in, right? And basically the idea is that there's only one way to go from an infalling to an escaping orbit, and that's by passing through one of these precise bound orbits. And so that just basically tells you that there has to be a critical curve that surrounds the infalling orbits, right? So there has to be sort of a circular shape. Well, it doesn't have to be circular, but there has to be a closed shape that surrounds all of the infalling orbits. Okay, I'm almost done. I have 2 more slides, and then I'm done. Don't worry. I just want to maybe, so that was the idea about, if I have separable metric, what's the most general kind of critical curve that I can generate? And now I want to just give a few ideas about, what about if I don't have separability? Right? Can I break the fact that this is a connected critical curve or not? And so we're also working on this. And so the idea here is that we're going to use a algebra that was constructed by these guys a few years ago on the geodesic phase space. And so for Kerr, they do this explicitly, and they show that there's an SL2 algebra on the geodesic phase space where the dilatation essentially pushes you onto the critical curve. Right? So the critical curve is a fixed point of this dilatation of the entire SL2 even, and the dilatation really pushes you on this, right? And so this, this goes under the name, right? They call this photon ring holography. We can, of course, discuss about this title, but the point for me is there's an SL2 algebra which is well defined everywhere. That's also important, which pushes you onto the critical curve. And so the first thing that we did, or that Oliver did, I should say, is extend this algebra with an extra generator that commutes with the SL2, but that moves along the critical curve, as you can see from these arrows here. And so it turns out that this exists. You can make a generator that goes along the critical curve everywhere, is also commuting with the SL2 everywhere, and it's unique. So there's a unique generator that moves along the critical curve and commutes with the SL2 everywhere. And so the idea, or the conjecture, is that we now have this SL2 cross R, right? So the SL2 that pushes you on the critical curve, and the R which moves you from one side of the critical curve to another. action. So this is an action. And why is it R? Well, it's really an infinite action, right? So from one side, right, I'm only talking about the upper half plane, but it's basically because the lower half plane is a mirror image, right? If you go from one corner to the other, that's an infinite amount, that's an infinite action of this group. So it's really an R action. And so our conjecture is essentially that, maybe it's possible in a non-separable space to have this little region of phase space where I can do the same game and define an SL2 cross R action. But if you can do this globally, meaning you can find an SL2 cross R algebra on the phase space of geodesics that is everywhere well defined, then this is going to be exactly equivalent with separability, right? And we have some arguments as to why, but I'll just leave you with that idea. Okay, so let me just conclude or wrap up. Again, the name of the game, right? What I'm interested in is asking ourselves a question. If I have something that is not Kerr, that is not captured by GR, right? What properties of the photon ring and black hole images in general are going to reveal this to us, right? And so, what properties can we look at and say this is really a test of GR in the sense that we can distinguish GR from other things? And so I focused in particular on this critical curve, which is sort of the limit of the photon ring, right? Underlying the photon ring. And I asked the questions, when is it connected and closed? And so what I said in the last part of my talk was, well, definitely when the geodesics are separable, it seems. But what about the inverse statement, right? Is the fact that it's connected and closed exactly equivalent to separability or not? That's still a bit of an open question. And then, if you do have one critical curve like this, and then we can talk about the shape of it. And when is the critical curve beyond Kerr, beyond GR? When does it fit in the same shape category, right? The circlips category. And so there, the let's say heuristic answer is usually, right? It's very hard to deviate from this Kerr shape. And in particular, right? Just measuring this precisely is not going to be the measure of does it break GR or not. If there's something that breaks the circlips shape, you'll see it already from other signatures. Okay, I'll stop there. Thanks.
About 5 minutes for questions or so. Any? Paolo?
Can you go back to the feet for the circle lips, whatever?
Stop me when I...
Yes, no, the first part, end of the first part, the 0.04% accuracy plot.
All the way here?
Yeah, here. So if I understand correctly, the coefficients of these feet are spin dependent for Kerr, right? So is there an estimate of taking this analytical expression, whether one can extract the spin and to which accuracy? So really remaining in the Kerr realm.
I don't think anybody's tried to... Okay, so your question is basically, if I measure this, so I measure these coefficients, can I extract the spin to some precision?
Because this plot is done, I presume, for a given spin, right?
Yeah.
But there will be some degeneracy between different spins, even within Kerr.
Yeah, so I don't think anybody's studied exactly that question, although maybe Alejandro can correct me if I'm wrong. But I would say there is a large degeneracy in spin and inclination, right? So it's not going to be obvious to, if this is the only measurement you have, I don't think it's going to be very obvious to disentangle what is the spin, what is the inclination, and other things.
Because that could be a proxy to beyond Kerr deviations. I mean, if you're not able to measure the spin accurately.
Yeah, that's right. Yeah. So one of the things that I've been told that they really want to do with the next space mission that will do better with this is to provide very accurate measurements of spin for a black hole. So something called the inner shadow, which, these pictures are really not clear, but there's always going to be, right, there's fuzz around the photon ring, but there's always going to be a very black region in the center here, which is called the inner shadow. And the details of that are very dependent, are very sensitive to spin. And so by measuring the inner shadow, for which you need you can't do that yet with the IPHT, that would give you a very precise measurement of spin. So you could maybe imagine combine that with, once you have a very precise measurement of the spin, you have a range of possible circlipses predicted by GR, right? Not all R1 and R2 are possible. And then you could imagine that gives you an even better test somehow, yeah.
Okay, wait. Can you wait for the...
I'll try.
Why do you expect a degeneracy with the spin? Because you have three parameters, no? The mass, the spin, and the angle
Right.
of observation. Then I would expect that you have three parameters, R0, R1, R2.
Yeah,
should
but
be
it's,
a
I mean,
unique,
just as a very simple example, right? If you see a circle, this could be either 0 spin or 0 inclination. Now you're looking at it on the spin axis.
You're saying that you cannot
So
measure the inclination for the spin? I would say yes. No?
from this, you cannot say you cannot make an unambiguous measurement of the inclination itself. No.
Any other? Toby?
Sorry, it may have been lost to me in the details, but earlier when you said that we were considering critical curves which could, in different black holes, have essentially like a range of radii or diameters, and then that would lead to corresponding, like, I don't know, photon rings with at least some kind of spread, rather than this like very thin ring that's just coating around sort of two the sort of event horizon or event horizons. How were you able to deduce the actual physical diameter of the black hole object from that?
So, so is your question, if I observe a photon ring, how do I know what the size of the black hole itself is?
Yeah, pretty much. Yeah.
Okay, so it's well, basically because the shape is very much constrained, and so also the size is very much constrained by GR. So if I look at this, I have a very, and I basically just measure the size of this guy. That's going to tell me the mass to a very good precision. So the simplest, cleanest example is Schwarzschild, right? If I have this, so that's the Schwarzschild critical curve, and that's a radius of square root 27m. So, measuring this tells me exactly, and I also need to know, of course, but this is always true, right? It's degenerate in, mass versus distance, right? So, you move a black hole further away, it's going to look smaller. So you need to know one of the two to be able to deduce the other, right? You can only look at like m over d, basically. Yeah. Does that make sense?
Yeah.
But basically, the size tells you m over d.
All right.
Yeah.
I had one quick question, but it's more intuitive. I would have expected a disconnectedness of the photon ring to be related to perhaps echoes, in the sense of, if you don't have echoes, I wouldn't expect disconnectivity, and if you have echoes, I might expect disconnectivity. Could there be such a link?
So echoes, you mean in like a gravitational wave signal?
When you ping the black hole with a signal, the question is, do things ever come back? And that's what I mean by an echo.
Yeah, okay. So
could there be a link between disconnectivity and echoes?
I mean, yes and no. So okay, here is an example of a black hole. So there shouldn't be any echoes. But you do see that there's something that looks like discontinuity. So in that sense, I would say it's not immediately related. But of course, it is true that whatever your bound orbit structure is, right, whatever your photon shell structure is, that determines your ring down signal, essentially, right? Because that's where, at least in the high frequency limit, for sure, it's basically geodesics, and so this is determining everything. But I think it's not a one-to-one relation. Like if I see this, I see echoes, certainly.
I think we should break for coffee. Let's resume at 11:35, and then let's get coffee and thank.